The Japanese dive bombers completed their attack run with deadly precision. 4 HD-3A aircraft had just struck their target. The New Zealand cruiser Achilles bore fresh wounds from their assault. Now they banked away from the American task force. The morning was January 5, 1943. The location was Cooler Gulf in the Solomon Islands. Lieutenant Red Cochran stood at his position aboard USS Helena. His hands gripped the fire control director of the American cruiser. What happened next would change warfare forever. Cochran's crew loaded shells containing revolutionary technology. The aft 5-inch battery prepared to fire. 2 salvos thundered across the tropical waters. The sound echoed between the islands. One departing Japanese aircraft suddenly erupted into flames. No direct hit had struck the plane. Shrapnel from a shell exploding 30 feet away tore the aircraft apart. The pilot died instantly. He never knew what weapon had killed him. His commanders would remain equally mystified. Japanese high command would never solve this puzzle. The mystery would persist until war's end. This represented the first combat kill by a weapon that would reshape military history. Military historians would later rank this technology alongside radar and atomic weapons. The proximity fuse had announced itself to the Pacific War. The deceptive code name was Variable Time, or VT Fuse. Over the following 30 months, this innovation would fundamentally transform Japanese tactical thinking. Their aerial offensive capability would be shattered. Thousands of American lives would be saved. The transformation began with a problem that had plagued gunners since aircraft first became weapons. Anti-aircraft fire had struggled with fundamental mathematical limitations. Pearl Harbor demonstrated this reality with tragic clarity. December 7, 1941, brought Japanese aircraft screaming through Hawaiian skies. American gun crews fought desperately with available weapons. 5-inch naval guns thundered from damaged ships. Shells flew skyward at attacking dive bombers and torpedo planes. Each shell required manual fuse setting. Sailors turned wrenches against clockwork mechanisms. Enemy aircraft dove through defensive fire. Most shells exploded uselessly in empty sky. Preset timers detonated them seconds too early or too late. Some shells never exploded at all. Others fell back to Earth with contact fuses still armed. 9 miles from the harbor, shells weighing 55 pounds crashed through Honolulu roofs. They detonated in streets. They tore through buildings. Civilian casualties mounted from American anti-aircraft fire. The Hirosaki family died when a 5-inch shell flew through their restaurant window. Breakfast service was underway. Father Jitsuo perished instantly. Sons Jackie and Robert died beside him. Daughter Shirley and nephew George were killed along with 7 young customers eating at the Cherry Blossom restaurant. 3-month-old Janet Yumiko Otter became the youngest casualty. A shell struck her home. It killed her, her mother, and her aunt simultaneously. By the time smoke cleared over Pearl Harbor, 68 civilians lay dead. 32 had been killed in Honolulu specifically. Japanese bombs had not killed them. Improperly fused American anti-aircraft shells landing in the city had caused their deaths. The tragedy illustrated the inadequacy of existing technology. Modern aircraft presented challenges that conventional gunnery could not solve. The mathematics were brutally unforgiving. Traditional anti-aircraft fire required 3 pieces of perfect information. These had to be executed in sequence under combat conditions. First, optical rangefinders calculated exact distance to targets moving at 300 miles per hour. Smoke, clouds, and tropical sun glare complicated these measurements. Second, height-finding equipment estimated altitude against fast-moving targets. Aircraft could climb or dive at will. Third, fire control computers calculated where aircraft would be in 15 to 30 seconds. This represented the time required for shells to reach altitude. Sailors then manually set clockwork time fuses. Shells were loaded. Guns fired. Fuse mechanisms counted down mechanically. If all calculations were perfect, if aircraft maintained course and speed, if mechanical fuses functioned correctly, shells would explode near targets. The odds of destroying aircraft were approximately 1 in 2,500 rounds fired. These were ideal conditions. In combat, with multiple targets maneuvering through defensive fire, odds dropped catastrophically. The problem had existed since World War I, but became critical as aircraft evolved. Aircraft in 1918 flew at 90 miles per hour. Altitudes remained below 15,000 feet. By 1940, modern fighters exceeded 400 miles per hour. Altitudes reached above 30,000 feet. The gap between gunnery technology and aerial performance had widened into a chasm. British forces discovered this reality facing German dive bombers over Dunkirk. Ships lacked space for additional guns. More ammunition consumed limited magazine space. Better fire control helped, but could not overcome fundamental limitations. Time fuses required perfect prediction of aircraft future positions. August 1940 brought Dr. Merle Anthony Tuve an impossible assignment. The Department of Terrestrial Magnetism at Carnegie Institution received the request. The National Defense Research Committee needed solutions. Tuve had been born in South Dakota. He was educated at University of Minnesota and Johns Hopkins. His career had been spent exploring ionosphere physics using radio waves. In 1925, working with Gregory Bright, he pioneered techniques measuring radio wave reflections from the ionosphere. This work mapped atmospheric structure. It laid theoretical foundations for radar development. When the committee approached him about developing proximity fuses for artillery shells, he understood immediately. Radio physics might provide the solution. The British had shared preliminary research during the Tizard mission. Their conclusion was pessimistic. A proximity fuse might work in rockets or bombs. The forces involved in artillery made it impossible. 5-inch shells experienced acceleration of 20,000 times the force of gravity when fired. No electronic device could survive such forces. Certainly not the delicate vacuum tubes that formed the only available electronic components in 1940. Tuve proposed something different. A miniature radio transmitter and receiver would be installed in shell noses. The device would be no larger than a pint milk bottle. The transmitter would broadcast continuously. As shells approached targets, radio waves would reflect back. Reflected signal frequency would shift due to Doppler effect. When frequency shift reached predetermined levels, indicating proximity to targets, electronic circuits would close. Current would flow to detonators. Main charges would explode. The first challenge was identifying components that working fuses required. Radio transmitters had to operate at frequencies providing usable Doppler shift. Receivers needed sensitivity to detect reflected signals from aircraft several hundred feet away. Electronic amplifiers would boost received signals. Circuits would compare transmitted and received frequencies and detect Doppler shift. Power sources had to provide sufficient voltage and current. Detonators would be triggered by electronic circuits. Safety mechanisms would prevent premature detonation. All components had to fit inside spaces approximately 8 inches long and 2 inches in diameter. Every component presented problems that seemed insurmountable. Vacuum tubes were the only electronic amplifying devices available in 1940. These were fragile glass envelopes containing delicate filaments and electrodes. Standard radio tubes were 6 inches tall. They weighed several ounces. The largest tubes manufactured for rugged applications were designed for mobile military radios. They could withstand 10 G of acceleration. Fuses required tubes surviving 20,000 G. At 20,000 G, 1-ounce tubes would weigh 1,250 pounds. This would last for the fraction of a second required for shells to travel down barrels. This was sufficient force to turn solid steel into fragments. October 1940 brought urgent requests from the National Defense Research Committee to laboratories across America. Western Electric Company and Radio Corporation of America were asked to develop miniaturized vacuum tubes. These had to be hardened for extreme acceleration. Sylvania developed specialized glass formulations. Raytheon experimented with tube designs featuring planar electrodes. These distributed forces more evenly. Engineers discovered that conventional assembly techniques produced tubes shattering instantly under high acceleration. Solutions required innovations in every aspect of tube design and manufacturing. Glass was modified with additives increasing strength while maintaining vacuum seals necessary for tube operation. Filament components were embedded in shock-absorbing materials. Electrode structures were redesigned using spot welding techniques. These created mechanical bonds capable of surviving extreme stress. By spring 1941, after thousands of design iterations, acceptable tubes emerged from production lines. They measured less than an inch in height. They could survive 20,000 G acceleration. The power source presented equally daunting challenges. Harry Diamond and Wilbur Hinman at the National Bureau of Standards developed an ingenious solution. Glass tubes filled with electrolyte solution were sealed with metal plates at each end. When shells were at rest, liquid remained in tube centers. It stayed isolated from metal plates. When fired, centrifugal force from shell spin forced electrolyte outward. It contacted small pieces of metal embedded in tube walls. Chemical reaction between electrolyte and metal plates generated electrical current. Batteries activated only when shells were spinning. This provided built-in safety mechanisms preventing premature detonation. May 6, 1941, marked a crucial test at Dahlgren Naval Proving Ground in Virginia. 6 prototype fuses built by the National Bureau of Standards team were loaded into air-dropped bombs. Tests were conducted over water. Radio transmitters activated successfully. Receivers detected reflections from water surfaces. Electronic circuits triggered detonators properly. All 6 bombs exploded at correct altitudes. Success validated the basic concept. However, bombs experienced only a few hundred G of acceleration when released from aircraft. Artillery presented challenges orders of magnitude greater. By June 1941, Section T had expanded to over 100 engineers, physicists, and ordnance specialists. A former automobile dealership in Silver Spring, Maryland, became the main laboratory. Security was so tight that neighbors speculated about mysterious activities behind blackout curtains. The cover story described research into optical instruments. Reality was a crash program to develop a weapon that Allied military leaders believed could alter the war's course. The development process revealed cascading engineering challenges. Antennas had to be small enough to fit in noses, while efficient enough to transmit and receive radio signals. Engineers developed ring antennas circling fuse bodies. Transmitter circuits had to generate radio frequency signals at 70 to 90 megahertz. Circuit designers created transmitter designs using just 3 vacuum tubes. Receiver circuits had to detect signals 1/millionth the strength of transmitted signals. Amplifier stages using 4 vacuum tubes provided sufficient gain. Doppler detection circuits compared transmitted and received frequencies. They closed electrical contacts when differences indicated proximity to targets. November 1941 brought the attack on Pearl Harbor. This transformed the Proximity Fuse project from important research to critical priority. The Navy had been skeptical that electronics could survive gun launch. Witnessing inadequacy of time fuses during the Pearl Harbor attack eliminated all doubts. Production contracts expanded from millions to hundreds of millions of dollars. Johns Hopkins Applied Physics Laboratory was founded on March 10, 1942, to centralize development. 5 companies received contracts to mass-produce fuses, following designs developed at APL. Crosley Corporation in Cincinnati received contracts. So did RCA, Eastman Kodak, General Electric, and McQuay Norris. Entire factories were committed to fuse production. Over 100 factories would ultimately participate. Components were produced for fuses containing approximately 130 miniaturized parts. The goal was 40,000 fuses per day by late 1943, 70,000 per day by war's end. Secrecy surrounding the project was absolute. Workers assembling components never knew what final products would do. Different companies manufactured different sub-assemblies. The designation variable time fuse was chosen specifically to mislead anyone learning of the project. The code word POSIT was used in military communications. Even after combat use began, captured fuses that failed to detonate were assumed to be advanced time fuses. Japanese and German intelligence never determined the true nature of the technology. August 12, 1942, brought comprehensive testing at Chesapeake Bay, Virginia. The cruiser USS Cleveland conducted the first test of production proximity fuses against drone aircraft. 3 radio-controlled target drones were launched to simulate aerial attack. Cleveland's 5-inch guns required fewer than 10 rounds to destroy all 3 aircraft. This occurred on the first day of testing. Naval authorities canceled the remainder of the 2-day test schedule. Mass production and fleet deployment were immediately authorized. Tests revealed dramatic improvements over previous methods. Over the previous 2 years, time-fused shells scored hits requiring an average of 2,500 rounds fired per aircraft destroyed. Proximity-fused shells destroyed aircraft with dramatically fewer rounds. This demonstrated 25-fold improvement in effectiveness. Production accelerated through fall 1942. The first combat-ready fuses reached fleet units in October. Cruiser Helena received 500 rounds of proximity-fused 5-inch ammunition. These were carefully distributed to prevent accidental disclosure if the ship was damaged. Instructions emphasized that proximity fuses were to be used only over water. Duds would sink beyond enemy recovery there. Gunners were trained but not told how fuses functioned. Initial fleet reaction ranged from skepticism to curiosity. The morning of January 5, 1943, resolved all doubts. Lieutenant Cochrane's salvos destroyed 1 dive bomber and damaged a second. Gun crews had achieved aerial kills without perfect prediction of target position. Manual fuse setting was eliminated. Complex calculations that had limited anti-aircraft effectiveness since the technology's inception were no longer required. Word spread through the fleet immediately. Ships that had received proximity fuses began using them in every engagement. Cruisers, destroyers, and battleships reported kill ratios far exceeding anything achieved with time fuses. Enemy pilots noticed something had changed, but could not understand why. By March 1943, 25% of all anti-aircraft ammunition issued to the Pacific Fleet contained proximity fuses. These rounds accounted for over 50% of all Japanese aircraft destroyed by naval gunfire. Proximity fuses proved 3 times more effective per round than conventional time fuses under identical conditions. Against fast-moving targets in night engagements, the advantage increased to 7-fold. Ships previously defended by walls of steel relying on volume of fire could now achieve aerial kills with fractions of ammunition expenditure. The effectiveness of proximity fuses triggered Japanese tactical changes that Allied intelligence observed but could not fully explain. Japanese aircraft began attacking from higher altitudes. They sacrificed bombing accuracy to remain outside effective range. Torpedo bombers approached at wave-top altitude, where radio reflections from ocean surfaces caused premature detonations. Dive bombers released at steeper angles to minimize exposure time. These adaptations reduced Japanese strike effectiveness while failing to restore advantages they had enjoyed earlier in the war. American ships continued shooting down Japanese aircraft at rates that made conventional attacks unsustainable. Admiral William Halsey credited proximity fuses with fundamentally changing the balance of power. Japanese torpedo bombers had been particularly effective in night attacks when visual tracking was difficult, and time fuses were nearly useless. With radar detection and proximity fuses, ships could engage aircraft effectively in total darkness. During 1943, despite using proximity fuses in only 25% of ammunition expended, over half of Japanese aircraft destroyed by anti-aircraft fire were killed by proximity-fused shells. October 1944 brought desperate measures to the Philippines. Japanese forces, facing inevitable defeat, implemented a strategy that would test American defenses to breaking points. Special attack units, officially termed Shinpu Tokubetsu Kogeki Tai, were organized. They became universally known as kamikaze. Deliberate suicide attacks against American ships began. The first organized kamikaze attacks struck during the Battle of Leyte Gulf. The tactic was born from desperation and Japanese recognition that conventional attacks had become ineffective. Experienced pilots had been systematically destroyed over 2 years of attrition. Replacement pilots received minimal training, insufficient for bombing and torpedo attacks requiring precision. Kamikaze attacks required only enough skill to keep aircraft pointed at targets. Proximity fuses proved essential against kamikaze attacks, though their effectiveness was complicated by the nature of the threat. Conventional attacks saw aircraft approach, release weapons, and attempt escape. Proximity fuses destroyed attackers at distances where damaged aircraft would miss targets. Kamikaze attacks removed the escape phase. Pilots flying damaged aircraft continued toward targets. Sometimes they survived long enough to crash into ships, even after sustaining damage that would have caused conventional attackers to abort. Solutions required concentration of fire that destroyed aircraft completely, rather than merely damaging them. Ships increased rates of fire. They created denser patterns of proximity-fused shells. They engaged targets at longer ranges. The destroyer USS Hadley and destroyer escort USS Evans operated as radar pickets. They faced 156 attacking aircraft on May 11, 1945. The engagement lasted 90 minutes. Hadley destroyed 12 aircraft before being struck by 4 kamikazes. These remained airborne long enough to crash into the ship despite being hit by anti-aircraft fire. Evans destroyed 23 aircraft before damage forced her withdrawal. Post-action analysis showed that proximity fuses had been indispensable. They destroyed aircraft at ranges where time fuses would have been ineffective. Without proximity fuses, both ships would certainly have been sunk in the first 30 minutes. Statistical analysis from the Pacific War documented effectiveness precisely. Between October 1944 and August 1945, American naval forces destroyed 278 Japanese aircraft using proximity-fused ammunition. Hanson Baldwin's analysis, in his authoritative study, showed that only 46 would have been destroyed using conventional time fuses under identical circumstances. The 6-to-1 effectiveness ratio translated directly to lives saved and ships kept in action. At Okinawa, where American ships faced the most intensive kamikaze operations of the war, proximity fuses accounted for significant percentages of Japanese aircraft destroyed. The majority of kills still came from combat air patrols and shorter-range automatic weapons. June 12, 1944, brought new challenges to the fields of northern France. While proximity fuses revolutionized naval warfare in the Pacific, restrictions had prevented their use over land. Unexploded fuses might fall into enemy hands there. German technical intelligence had proven capable of reverse engineering captured equipment. The V-1 flying bomb campaign against London forced reconsideration. Beginning June 13, 1944, Germany launched thousands of V-1 cruise missiles at England. Over 120 per day flew at the height of the assault. Traditional anti-aircraft defenses struggled against targets traveling at 400 miles per hour at altitudes below 2,000 feet. Churchill personally authorized use of proximity fuses against V-1s despite risks of technology disclosure. Modified fuses were rushed into production at Crossley Corporation. They were flown across the Atlantic by special Lancaster bomber flights. British 3.7-inch and American 90mm anti-aircraft guns began firing proximity-fused ammunition against incoming V-1s in mid-July 1944. The effect was immediate and overwhelming. During the first week, kill rates increased from 10% to 24%. By the fourth week, 79% of V-1s were destroyed by proximity-fused anti-aircraft fire. On one day toward the end of the campaign, radar detected 104 V-1s approaching England. Proximity-fused anti-aircraft guns destroyed 68. Of the remaining 36, fighter aircraft destroyed 32. Only 4 reached London. The British capital was saved by technology developed on the other side of the Atlantic. December 16, 1944, brought Germany's final major offensive in the West to the Ardennes forest of Belgium. German forces launched attacks through terrain considered impossible for armor. The Battle of the Bulge caught American forces by surprise. Weather-grounded air support. Colonel George Axelson commanded the 406th Artillery Group at Monschau, Germany. He made an unauthorized decision that day. Facing massed German infantry assault, he ordered his gunners to use proximity fuses in ground combat. This violated strict prohibitions against land use. He decided the emergency trumped restrictions. 3 days later, on December 19th, General Dwight Eisenhower formally requested authorization to use proximity fuses in ground operations. All restrictions were removed on December 21, 1944. The effect on German forces was catastrophic. Traditional artillery fired shells that buried themselves in mud or snow before exploding. Energy was directed downward. Fragment distribution was limited. Proximity-fused shells detonated 20 to 50 feet above ground. They showered fragments over areas 50 times larger than ground-burst shells. German infantry advancing through open areas found themselves subjected to air bursts. No foxhole or trench could protect against these weapons. Each shell created lethal fragment patterns covering over 3,000 square feet. This compared to 60 square feet for conventional ground-burst shells. General George Patton's Third Army received priority allocation of proximity-fused ammunition. He documented the devastation personally. On the night of December 25th, his artillery caught a German battalion attempting to cross the Sauer River near Echternach. A single battalion firing proximity-fused shells killed 702 German soldiers by actual count. Patton wrote to the War Department about his observations. "The new shell with the funny fuse is devastating. We caught a German battalion which was trying to get across the Sauer River with a battalion concentration, and killed by actual Count 702. I think that when all armies get this shell, we will have to devise some new method of warfare. I am glad that you all thought of it first. Between December 1944 and March 1945, from the Battle of the Bulge to the crossing of the Rhine, proximity-fused artillery shells calibrated for airburst detonation took fearful tolls. Advanced fire control radar enabled artillerymen to destroy targets on reverse slopes of hills and beneath forest canopy where conventional fire was impossible. The Germans captured approximately 20,000 proximity fuses when they overran an American ammunition dump during the Battle of the Bulge. German ordnance experts examined the fuses but concluded they could not possibly function as intended. Technical specifications seemed impossible. Electronics that could survive artillery launch forces were considered beyond current technology. The Germans assumed the fuses were advanced time mechanisms they did not fully understand. The fuses were warehoused and eventually abandoned as German forces retreated. The secret remained secure not through security measures but through German disbelief that the technology could exist. March 1945 brought American forces preparing to assault Iwo Jima's heavily defended positions. VT proximity fuses were modified for use in bombs dropped from aircraft. The fuses detonated several feet above ground, creating airbursts over enemy positions. B-24 Liberator bombers dropped proximity-fused bombs on Japanese anti-aircraft positions before Marines landed. Results exceeded expectations. Airburst detonations caught Japanese gunners in the open. Equipment that would have remained undamaged by near-miss ground bursts was destroyed. By August 1945, over 22 million proximity fuses had been manufactured. Cost exceeded $1 billion in 1940s currency. Each fuse contained 130 miniaturized electronic components. The supply chain involved 87 firms using 110 factories. Crosley Corporation, RCA, Eastman Kodak, General Electric, and McQuay Norris served as primary assembly contractors. Over 2,000 suppliers provided components. At peak production, the American electronics industry manufactured 70,000 fuses daily. Cost per fuse dropped from $732 in 1942 to $18 by 1945. Production techniques improved. Economies of scale took effect. Secretary of the Navy James Forrestal stated after the war that the proximity fuse helped blaze the trail to Japan. He noted that without the protection this device provided to surface ships, the westward advance could not have been so swift. The cost in men and ships would have been immeasurably greater. Admiral Arleigh Burke served as Chief of Staff to Admiral Mark Mitscher, commanding fast carrier task forces. He recalled that all 5-inch ammunition in 1945 was fitted with proximity fuses. Those fuses knocked down enemy planes by the dozens. They prevented ship losses and casualties that would have been enormously larger without this technology. British Prime Minister Winston Churchill noted that proximity fuses made in the United States proved potent against the V-1 rockets that assailed Britain in 1944. The Japanese never fully understood why American anti-aircraft effectiveness had increased so dramatically after early 1943. Post-war interrogations of Japanese military officials revealed that most believed Americans had developed superior fire control radar. Others thought they had integrated aircraft detection with gun directors in ways Japan could not match. Some Japanese engineers speculated about radio-controlled shells, but dismissed the concept as technically impossible given forces involved in gun launch. The idea that individual shells could carry miniaturized radar systems seemed beyond credible technology. This failure of imagination allowed the proximity fuse to remain operationally secret throughout the war. the human cost of Japanese failure to develop equivalent technology was substantial. Japanese naval aviation lost over 12,000 aircraft in combat during the war. Documented evidence shows proximity fuses accounted for destroying several hundred of these aircraft directly through anti-aircraft fire. Each aircraft represented not just material loss, but trained aircrew impossible to replace. The death of experienced pilots in 1943 and 1944 forced Japan to commit poorly trained replacements. These fell victim to American defenses at unsustainable rates. By 1945, Japan resorted to kamikaze tactics, partly because conventional attack methods had proven ineffective against American ships equipped with proximity-fused ammunition. The broader impact of proximity-fused technology extended beyond World War II into modern military development. Techniques developed for miniaturizing electronics and hardening components to survive high acceleration became foundational for subsequent advances. Missile guidance systems benefited from innovations pioneered by the proximity fuse program. Space exploration utilized these developments. Modern artillery incorporated these advances. The concept of distributed intelligence, where individual munitions carry sophisticated sensors and processors, traces directly to VT fuses. Modern smart munitions that sense targets, discriminate between targets, and optimize detonation represent evolution of principles established between 1940 and 1945. Dr. Merle Tuvey returned to the Carnegie Institution after the war. He rarely spoke publicly about his role developing proximity fuses. When details were finally released, Tuvey deflected personal credit. He emphasized contributions of hundreds of engineers and thousands of production workers who transformed theoretical concepts into millions of reliable fuses. His modesty understated his essential leadership in a program that War Department officials ranked second only to the atomic bomb in strategic importance. Without his insight that radio proximity detection could be miniaturized sufficiently for artillery shells, the proximity fuse would have remained theoretical. Without his persistence through early failures when success seemed impossible, combat reality would never have emerged. The production achievement equaled the technical accomplishment. Manufacturing 22 million proximity fuses, each containing 130 precision components, required industrial organization on unprecedented scale. Over 100 factories had to coordinate delivery of components, matching specifications measured in thousandths of an inch. Supply chains had to deliver vacuum tubes, batteries, and electronic components from hundreds of specialized suppliers. All had to be synchronized to keep assembly lines operating at capacity. At 70,000 fuses per day, production required approximately 9 billion total electronic components over the course of the war. The proximity fuse stands alongside radar and penicillin as one of a handful of technologies that materially affected World War II's outcome. Unlike radar, whose development occurred in multiple countries, the proximity fuse resulted from deliberate application of existing knowledge to a specific problem. Dr. Tuvey and his team at Section T identified what needed to be done. They determined how to accomplish it. They executed a program that achieved operational capability in under 3 years. This focused approach to weapons development became the model for Cold War military research. The Manhattan Project developing atomic weapons followed similar organizational patterns. Post-war missile programs adopted the same structure of university laboratories, industrial contractors, and military oversight. The legacy of those 20,000 G-rated fuses extends beyond their combat effectiveness. It influenced how nations organize scientific talent for military objectives. It affected how industries manufacture precision electronics at scale. It demonstrated how seemingly impossible technical challenges yield to sustained effort, backed by adequate resources. The miniaturized vacuum tubes that seemed impossible in 1940 became routine by 1945. Precision manufacturing that required specialized technicians became automated as production techniques advanced. But in 1943, 1944, and 1945, as Japanese aircraft fell from the sky, as German infantry died under precisely timed airbursts, as V-1 missiles disintegrated over the English Channel, the proximity fuse represented the cutting edge of what human ingenuity could achieve. Lieutenant Red Cochrane watched that first Japanese dive bomber disintegrate on January 5, 1943. He understood that something fundamental had changed in aerial combat. His gun crew had destroyed an aircraft without perfect aim, without precise fuse setting, without any of the calculations that had limited anti-aircraft effectiveness for decades. The shell had done the work. It sensed the target. It timed its own detonation. It achieved what human gunners could only approximate. In that moment off Guadalcanal, a new era in warfare had begun. The age when individual munitions carried intelligence sufficient for autonomous operation had arrived. The story of the proximity fuse proves that sometimes the greatest victories are won not through destruction, but through demonstration. Not through propaganda, but through prosperity of ideas. Not through hatred, but through application of scientific method to brutal realities of modern warfare. German soldiers and Japanese airmen who faced proximity fuses never understood what killed them. They reported only that American defenses had become impossibly accurate. Ships seemed able to shoot down aircraft regardless of maneuvering. Artillery created explosions that seemed to seek targets with supernatural precision. The proximity fuse did not win the war alone. No single technology did. But it contributed to victory in ways that saved thousands of American lives. It accelerated Allied success by making aerial offensive operations unsustainable against well-defended targets. Those 20,000 G-rated fuses each represented the technological limits of 1940s science. They turned American artillery into weapon systems that enemy forces never expected and could never effectively counter. They remain testaments to what free societies can achieve when scientific curiosity, industrial capacity, and strategic necessity align in pursuit of common goals, worthy of such extraordinary effort and innovation. The shells that Lieutenant Cochrane's crew fired that January morning carried more than explosive charges. They carried the concentrated efforts of thousands of scientists, engineers, and production workers. They embodied years of research, months of testing, and weeks of manufacturing precision. They represented democracy's ability to mobilize intellectual resources for decisive military advantage. Each fuse contained vacuum tubes smaller than postage stamps, yet capable of surviving forces that would crush solid steel. Electronic circuits computed Doppler frequency shifts in microseconds. Antennas broadcast and received radio signals while spinning at thousands of revolutions per minute. Power supplies activated from centrifugal force generated electricity under conditions no peacetime device had ever faced. The Japanese pilot diving away from USS Helena that morning never knew he was flying into the path of a technological revolution. His aircraft was detected by radio waves transmitted from the approaching shell. Reflected signals were received, amplified, and processed by electronic circuits occupying less space than a cigarette pack. When frequency analysis indicated optimal proximity, electrical circuits closed with mechanical precision. Detonation occurred at exactly the distance calculated to maximize fragment effectiveness. The pilot died before sound of the explosion reached him. His commanders would spend months trying to understand what new American defensive technology had achieved such unprecedented accuracy. Intelligence reports described impossible gunnery performance. Ships were destroying aircraft at ranges previously considered ineffective. Night attacks that had been Japanese specialties became suicide missions. The psychological impact on Japanese aircrews was as devastating as the physical destruction. Pilots who survived encounters with proximity-fused anti-aircraft fire returned with reports their commanders found difficult to believe. American ships seemed to know exactly where attacking aircraft would be. Shells exploded with uncanny timing. Fragments found targets that seemed beyond reach of conventional anti-aircraft fire. The mystery deepened when captured American shells were examined by Japanese technical specialists. The fuses appeared to be conventional time mechanisms. No Japanese engineer suspected that individual artillery shells could carry active electronic systems. The concept seemed beyond technological possibility, given the forces involved in gun launch. This failure of imagination protected the proximity fuse's operational security more effectively than any classification system. Japanese and German intelligence agencies never developed comprehensive understanding of the technology they faced. Their tactical adaptations were based on observing effects rather than understanding causes. Aircraft began approaching American ships from different angles. Altitudes were varied to confuse range estimation. Attack patterns became more complex to reduce predictability. None of these measures restored the effectiveness that Japanese naval aviation had enjoyed earlier in the war. The proximity fuse had fundamentally altered the mathematics of aerial warfare. Where previous anti-aircraft fire required perfect prediction of target location at future moments, proximity fuses needed only to pass within lethal range. Margin for error increased dramatically. Kill probabilities improved by factors that Japanese tacticians could not comprehend. American gunners noticed the difference immediately. Training requirements decreased. Accuracy improved. Ammunition expenditure dropped while kill rates increased. Ships previously vulnerable to determined aerial attack became floating fortresses capable of destroying attackers at previously impossible ranges. The technology spread through American naval forces as production capacity increased. By mid-1943, every major combatant ship carried stocks of proximity-fused ammunition. Usage policies evolved from emergency-only restrictions to standard employment against all aerial threats. Gun crews developed tactics, maximizing proximity fuse effectiveness. Barrage fire created walls of fragments that attacking aircraft could not penetrate. Coordinated salvos from multiple ships produced overlapping zones of destruction. Individual aircraft survival rates dropped below levels that made conventional attacks tactically viable. Japanese naval aviation entered a death spiral from which it never recovered. Experienced pilots were systematically eliminated by increasingly effective American defenses. Replacement pilots received shortened training due to fuel shortages and time pressures. These poorly prepared aircrews fell victim to American defenses at unsustainable rates. The cycle accelerated through 1943 and 1944. Each engagement cost Japan irreplaceable aircrew, while American defenses became more sophisticated. Radar integration with proximity-fused anti-aircraft fire created defensive systems capable of engaging targets in all weather conditions. Night attacks that had been Japanese tactical advantages became killing fields where American ships could destroy attackers without visual contact. The combination of radar detection, computer-assisted fire control, and proximity-fused ammunition eliminated traditional advantages that attacking aircraft had enjoyed under darkness. By 1945, Japanese tactical doctrine had been forced to abandon conventional bombing and torpedo attacks in favor of kamikaze operations. This desperate measure represented acknowledgement that traditional methods could not overcome American defensive capabilities. Even suicide attacks faced proximity-fused defenses that destroyed aircraft before they could reach their targets. The proximity fuse's impact extended beyond direct combat effectiveness to strategic implications that shaped the war's final phase. Japanese inability to sustain effective aerial operations against American naval forces accelerated the collapse of their defensive perimeter. Island bases could not be reinforced or supplied when transport aircraft faced insurmountable defensive fire. The technology that began with Lieutenant Cochrane's successful engagement off Guadalcanal ultimately contributed to Japan's strategic defeat by making aerial resupply operations impossible. The mathematical precision of radio proximity detection had evolved into strategic advantage that enemy forces could not overcome through tactical adaptation or operational innovation. Those shells fired on January 5, 1943, announced more than a new weapon. They heralded the age of smart munitions, where individual projectiles would carry sufficient intelligence to make autonomous targeting decisions. The proximity fuse represented the first step toward modern precision-guided weapons that would dominate military technology for generations to come.